Hi everyone. Thanks very much for attending my talk. This is Shuguang Han from Google Research. Today I'm going to talk about our recent efforts on building an adversarial bandits policy for crawling commercial web content. This is a collaborative work between our team from Google Research and Google Shopping team from Zurich. This is a typical example of commercial web page that sells Google Home. Throughout the whole presentation, we will denote such a page as an offer page. The crawling of offer pages enable us to extract important product attributes such as price, availability, and image. Such information will be used to serve search queries with shopping intent in Google search. In this paper, we only focus on the price information where we believe other attributes such as image and availability will share similar properties. This looks like a simple task, but we encountered a lot of challenges when we were actually doing that. First of all, we see that a lot of offers change their prices, particularly on holidays and promotional seasons, so that crawling only one time is not enough. However, scheduling frequent recrawls are also impractical because of the limitation of crawling resources. In our particular case, we have billions of offers in our database, and we essentially cannot recrawl all of them in daily basis. At the same time, we also want to avoid overwhelming the same host. We do think about simple solutions such as asking merchants to provide their price change update information. However, small merchants usually do not have capacity of doing such a task. Even for large merchants, there is no guarantee that they will immediately update their price information after certain offers change their prices. As a result, in this paper, we are seeking for a more intelligent recrawling strategy that uses machine learning. Before we dive into the technical details, let's first define our problem and evaluation metrics. Suppose we have an offer, it has a price change at a certain time, and later on we need to make a crawl decision. If we crawled and then updated the price in our local database, in later clicks, users will see the right information. Otherwise, users will see the outdated price information. Here, we define the click-weighted freshness metric, which is measured by the proportion of clicks users will see the right price information. With this metric, we can then formalize our problem as seeking for a crawling policy P, so that under this crawl policy, our click-weighted freshness metric is maximized. At the same time, it is also subject to the resource budget B. Here, each PI indicates a probability to crawl one offer I at a certain time. Now let's move back and discuss how can we develop a more intelligent recrawling strategy. The existing practices can be summarized into the following three categories. The uniform strategy that tries to crawl all of the offers with a uniform probability. The proportional strategy that attempts to crawl offers proportionally to a certain attribute. For example, one might want to crawl offers relatively to their change rate delta, because we only care about the offers that has price change. You may also want to crawl offers relatively to their click rate mu and impression rate nu, because the click-weighted freshness metrics only care about the offers that will be clicked in the future. More recently, Arthur and his colleague proposed a more advanced recrawling strategy called lambda crawl, which models a recrawling task as a constraint optimization problem, and then they provided a closed form solution for the theoretically optimal crawling rate, which is shown in the below formula. I'm not going to explain the details about this formula, but please remember that The optimal crawling rate, rho I, depends on two factors, the click rate, mu I, and then change rate, delta I. So the overall message from this formula is that we should crawl those likely changed and likely clicked offers, but at the same time, we should also penalize offers that change too frequently, because for those offers, no matter how frequently you recrawl them, their price might be changed in the next minute. If you want to know more details about lambda crawl, you can go to this page from Azar and his colleague in PNAS 2018. Okay, most of these above recrawling strategies actually assume the knowledge of the impression rate, the click rate, and then the change rate, which were actually unknown beforehand. To obtain such information, the simplest approach is to estimate from the past 30-day past history. For example, you can use the historical frequency from the past 30 days. However, this might be inaccurate because of data sparsity. For most of the offers, we only crowd them 1 or 2 times a month. To achieve a better prediction, we propose the neural predictive models that combine both historical features and metadata features. More specifically, metadata features such as product brand, product category, product title, merchant IDs, hour of day and day of week will be encoded with using embeddings and then further combined with the dense historical frequency information. Both of those features will be fed into deep neural nets for prediction. If you want to know more details about this model, you can refer to our paper from the last year. So to build our predictive models and to further understand the effectiveness of different recrawling strategies, we need a dataset that contains ground truth labels. This cannot be simply extracted from existing production crawl logs because, as I mentioned before, most of the offers were only crawled 1 or 2 times a month. For this reason, we created the Celtics dataset in which we sampled 1 million offers from our database. And then we schedule hourly recrawls for all of those offers. In this way, the data provides us a full observability of price history for all of those 1 million offers. From May 2018 to April 2019, we have connected billions of crawls for those offers. With the Celtics dataset, we can then split the data by time and then build the training examples and testing examples for our predictive models. And we can also use such a dataset to simulate and to evaluate the effectiveness of different recrawling strategies. Let's first look at the predictive model performance. In this paper, we model the prediction tasks as binary classification problems in which we try to predict whether an offer will change its price, whether an offer will be clicked or impressed in the next day. In the below table, we have experimented 3 different models on these 3 different tasks. In the first model, we only use history features from the past 30 days. And then in the second model, the second row, we only use the metadata features, and then we build a deep neural net on top of these features for prediction. In the third row, we combine both metadata features and history features. So our evaluation is built on top of ROC-AUC metric. According to this table, you can see that combining metadata features and history features actually help improve the AUC metrics, particularly on the price change prediction, so that this feature combination will be set as a default for our neural predictive models. Okay, now let's look at the evaluation results on the click-weighted freshness metric. In this table, we consider 3 groups. the uniform group that crowds all of the offers at a uniform probability, the history group that involves a set of recrawling strategies with their parameters such as click rate, change rate, impression rate estimated from the past 30-day histories. We also include a predictive model group which estimated all of the above parameters from our neural predictive models. Each column here indicating a resource budget. 10% means we can only crawl 10% of the offers. 20% means that we can only crawl 20% of the offers, and so on and so forth. In terms of the results, we have several important findings. First of all, we find that the recrowding strategies that build on top of our predictive models outperform the same approach with the parameters estimated from the past 30-day histories. We also find that lambda crawl does outperform other proportional recrawling strategies, but most importantly, we find that the lambda crawl built on top of our neural predictive models outperform all other recrawling strategies. This again demonstrates the usefulness and the effectiveness of our neural predictive models. Also from the above table, we find that lambda crawl does effectively combine the click rate and change rate. If you still remember the lambda crawl formula I mentioned before, in which a lambda crawl actually combined the click rate mu and change rate delta. However, lambda crawl does not include the impression weighted strategy, which according to the above table actually performed pretty well. Also, lambda crawl does not include the uniform strategy, which based on many of previous studies actually can boost the offer level freshness by a very large margin. In addition to that, the parameter estimations are not always perfect. In our task, the overall AUC is only around 0.88, and it is highly biased towards the popular offers, so that one might want to reduce the risk of only relying on one single recrawling strategies. For this reason, we propose to integrate multiple recrawling strategies using a K-armed adversary bandits policy, KAB for short. Here is a simple illustration of our proposed K-armed adversary bandits with 5 candidate strategies. These 5 strategies includes lambda crawl, change weighted recrawling strategy, impression weighted crawling strategy, click weighted strategy, and then uniform strategy. In the very beginning, we set the arm selection probability to be uniform, and then in each timestamp, we pick one arm based on this probability distribution, and then make crawling decisions based on the choosing arm, and then compute the increase of click-weighted freshness as a reward. Using this reward, we then recompute the arm selection probability. In this particular case, you will see that with time passing by, the click-weighted strategy and the lambda crawl will be selected more often than the other strategy because they were getting higher and higher probability. So with time going on, this probability distribution will be more stable. In terms of the implementation, we adopted the standard EXP3 algorithm that were described in this paper in 2002, but we highly customize this approach based on our task settings. Okay, here are the results, evaluation results on our proposed KAB policy. Here we only include lambda crawl that use our neural predictive models for parameter estimation for the baseline, because this is the best approach we have so far. So in this table, we find that our proposed KAB approach actually outperform all outperform the lambda crawl over all of the resource budget from 10%, 20% to 90%. In addition to that, we also evaluate the KAB5 approach on top of the offer level freshness metric. Here, the offer level freshness is measured by the percentage of offers that have the right price information, regardless of whether the offer was clicked or not. Based on the below table, we also find that KAB5 policy actually outperform lambda crawl across all of this resource budget. Okay, so in the production system, usually we have a very tight budget. Even, for example, in our particular case, since we have billions of offers, in daily basis, we cannot even crawl 1% of those offers. To understand how our proposed KAB approach performs under the tighter budget, we vary the resource budget from 0.1% to 0.9%, 1% to 9%, and 10% to 90%. And then we plot the freshness increase over lambda crawl on both click-weighted freshness and offer-level freshness. The results for click-weighted freshness is on the left diagram and offer-level freshness on the right diagram. Here, the horizontal axis denotes a resource budget from 0.1% to 1% to 100%. This is in log scale. The vertical axis denotes the relatively increase of freshness metric over lambda crawl. So a positive means our approach outperformed lambda crawl. A negative means our approach is worse than lambda crawl. From these two diagrams, we see that the lines are all above zero, indicating our proposed KAB5 approach actually outperform lambda crawl over all of this resource budget. To further understand the effectiveness and the usefulness of each candidate arm, we also evaluating over different KAB policies. Particularly, we experiment in KAB2, which only include the click-weighted strategy and change-weighted strategy. And then we further introduce a uniform strategy for KAB3, and then we introduce an impression-weighted strategy for KAB4. The KAB5 is exactly the same as what we described before. And in the right diagram, we plot the freshness increase over lambda crawl for all of these KAB policies over the click-weighted freshness and offer-level freshness. Again, here, the horizontal axis indicates the resource budget from 10%, 20% to 90%. And the vertical axis denotes the freshness increase. Again, the positive value means it outperformed lambda crawl. Negative value means it is worse than lambda crawl. So based on the above two diagrams, we have several interesting findings. First of all, we find that the KAB approach actually can achieve comparative experiments performance even without lambda crawl. If you look at this KAB3 and KAB4. Also, we find that adding the uniform strategy helps both freshness metrics. If you look at the KAB3, KAB4, and KAB5, also we find that including lambda crawl helps further boost the offer level freshness, but not too much on the click-weighted freshness metric. To summarize the results, so first of all, in this paper, we propose the formalization of this content recrawling problem, which actually can be generalized to other crawling domains and even the domains beyond crawling. We also propose a neural predictive models for change prediction, for click prediction, for impression prediction, which obtain better prediction performance and which can also lead to better recrawling performance. Third, we also propose an effective KM bandits policy for recrawling, which outperform the state-of-the-art recording strategies, and is also robust to very tight budgets. Okay, so that summarizes the presentation. Thanks.